Hello everyone, I'm Daniel. I'm going to present my latest paper titled Dynamic Home Care Routing and Scheduling with Uncertain Number of Visits per Referral. This was my postdoc project advised by Jonathan Patrick and Anton Sauer, and it was recently accepted for publication in the Transportation Science Journal. I have provided the link to the paper and the PDF link on Arxiv in the description of this video. Let's start with the problem definition. The percentage of the elderly population worldwide, specifically in Canada, is growing rapidly. In July 2023, 18.9% of Canada's population was 65 or older. The global average for this age group in 2022 was 10%. That's where home care becomes important. It includes medical, paramedical, and social services provided to patients in their homes. It offers less expensive and more flexible services compared to those in hospitals or long-term care facilities. Consequently, these factors has made home care one of the fastest growing industries in the world. In our model, we assume there are k different service types, one of which is assigned to each referral upon arrival. Each service type K is characterized by the following features: a service time per visit denoted by EK, a care pattern shown by HK representing the number of days between consecutive visits, a probability distribution function for the number of visits denoted by J hat K, and a wait time target shown by TK indicating the number of days an accepted referral can wait for the first visit. We investigate the home care routing and scheduling problem for a single nurse. Decisions include accepting or rejecting each new referral, assigning the first visit of each accepted referral to a day within its wait time target, determining overtime for each day, determining diversions for each day. Diversions are visits assigned to on-call nurses due to nurse capacity limitations, incurring a much higher cost. And the final decision is routing the visits assigned to the nurse each day. Each new home care request represents a referral with one or more likely several visits following a specific pattern, such as one visit every day or every other day. New referrals arrive dynamically each day, and we only know the distribution of number of arrivals for each region and service type. The exact number of visits per referral is unknown due to factors like the uncertain speed of recovery or unexpected changes in service type. We only know the distribution of the number of visits for each service type. After visiting a patient, it can be determined whether at least one more visit is needed. And once a referral is accepted, the remaining visits until discharge are confirmed and must be delivered. In our model, we consider a grid area on the map that includes multiple regions. The center of each region is assumed to be a proxy location for all postal codes in that region. The depot or nurse's home is placed at the corner of a region. We use Manhattan distance because it more accurately represents the actual distance traveled by a vehicle or pedestrian in urban environments. Additionally, the grid area can be asymmetric. To further clarify our decisions, I categorize them into two parts and illustrate them here. The first part concerns the acceptance or rejection of new referrals, and if a referral is accepted, which day we assign the first visit. In this example, we have two service types, and the characteristics of each service type are given in the first table. Let's assume that we are at the end of December 31 and have 3 new referrals from locations 7, 9, and 21. We accept referral 1 and assign it to day 1, but we are only certain about the first visit. The number of visits can range from 1 to 3 times the expected number, means 24 visits. Referral 2, which is far from depot, is rejected. The service type for referral 3 is 2, and the wait time target for service type 2 is 3 days. Referral 3 is accepted and assigned to day 2, which is within the wait time target. Moreover, the care pattern for service type 2 is every other day, so visits for referral 3 are scheduled accordingly. The second part of the decisions involves how to service visits assigned to a day. In the grid area, you can see 3 yellow regions where patients need to be visited today. For each region, this number indicates the region number, and this one represents the number of patients to be visited in that region. The nurse has a regular shift length and maximum allowable overtime. The unit travel time is shown by an orange rectangle representing the travel time between 2 adjacent locations. The unit service time is shown by a red rectangle representing the service time for a single visit. Okay, so the nurse starts from depot and services 2 patients in region 11. Then she goes to region 18 and services 5 patients there. You can see that the nurse has already surpassed the regular shift and used part of the overtime. The remaining overtime capacity is insufficient to visit the remaining 2 patients in region 4. Therefore, the nurse returns to the depot, and these 2 patients are serviced by an on-call nurse. The overtime cost depends on the overtime work. On the other hand, the diversion cost per visit depends on the service time of that visit and is independent of the on-call nurse's travel time, assuming there is always an on-call nurse close to any region. Now I talk about the Markov decision process, or MDP model. An MDP models decision making in discrete, stochastic, sequential environments. We consider a discounted infinite horizon MDP. The basic components of an MDP include decision epochs, states, actions, costs, and a state transition. We assume that no new referral requiring a same-day visit occurs in the middle of the day. Therefore, the decision epoch occurs once a day at the end of the day and before the start of the next day. We assume a rolling planning horizon of T days, which allows us to track the next visit of each patient within this horizon. Below is an illustration of a rolling planning horizon of 5 days and 2 consecutive decision epochs. States have 2 main elements: XTKLJ representing the number of patients of service type K in location L with J visits completed before day T, and J plus 1's visit already assigned to day T. YKL represents the number of new referrals of service type K from location L waiting for a decision. Here's an illustration of the state variables X. We have 3 colors: gray for completed visits, green for a certain next visit, and yellow for a probable future visit. Suppose all patients are of type K and from location L, where the service type K has a maximum of 4 visits and a care pattern of 1. Patient 1 contributes 1 to the variable X1KL3 at the current decision epoch. The first index T equal to 1 means the next immediate visit has been assigned to day 1, and the last index J equal to 3 indicating 3 visits have been completed previously. Patient 2 contributes 1 to the variable X1KL2 with the first index being 1 because the next immediate visit has been assigned to day 1, and the last index being 2 because 2 visits were completed previously. Since only the next visit of a patient exists in the schedule at any time in our model, this patient doesn't contribute to any other X variables. Therefore, XTKLJ for the set of indexes defined as capital theta is always 0. Patient 3 contributes 1 to x3KL0. Here, index t is 3 because the next visit is assigned to day 3, and index j is 0 because no visits have been completed before this visit. At each decision epoch, the scheduler takes an action A comprising 5 elements. Rk represents the number of new referrals of type K from location L that are rejected. NTKL denotes the number of accepted referrals of type K from location L whose first visits are assigned to day T. ZKL gives the total number of visits of type K from location L that are diverted. O represents the order of visiting the regions in a day. And finally, U indicates the amount of overtime the nurse should work today. In the following, I explain the constraints defined for the state and action variables. According to constraint 2, the number of rejections of each type for each location equals the number of new referrals minus the number of accepted referrals. Constraint 3 states that the number of diversions of each type for each location is less than or equal to the corresponding number of visits assigned to day 1. According to constraints 4 and 5, we set WL equal to 1 if there is at least one patient in location L that must be visited by the nurse on day 1. Constraint 6 ensures that the total travel time from the depot to each location L, shown by FL, is at least equal to the direct travel time from the depot to that location. Based on constraints 7 and 8, the total travel time from the depot to each location is greater than or equal to that of its preceding locations in the nurse's route, plus the travel time between the corresponding locations. The nurse's total travel time on day 1, shown by Q, is obtained from constraint 9, and it guarantees the return of the nurse to the depot at the end of the route with the addition of DL0. Based on constraint 10, the tour length on day 1, shown by G, is equal to the total travel time plus the total service time of all patients visited by the nurse on day 1. According to constraint 11, G does not exceed the regular shift length of the nurse plus overtime, and constraint 12 imposes the maximum allowable overtime shown by chi prime. Okay, now let's get to the state transition. A transition from a state S to a state S prime, which represents the state right before the start of the next day, depends on the chosen action for the current day and 2 stochastic elements: the number of new referrals and the number of patients visited on the current day who need at least one more visit. Let's define some terms first. PKJ plus 1 is the probability that a patient of type K will need at least one more visit after receiving J visits. BXP is a binomial random variable with X being the number of trials and P the success probability. On the current day, this number of patients received their first visit and this number received their later visit. Therefore, the number of patients served today who require at least one more visit can be represented by these binomial random variables. Here's an illustration. Consider a patient with a maximum of 3 visits and a care pattern of 2. The first visit assigned to January 1st, the first day of the current decision epoch. Therefore, this patient has contributed 1 to one of X1KL0 or N1KL. In the next decision epoch, January 2nd, becomes the first day of the planning horizon. For the same patient, the first visit was done yesterday, and the second visit was assigned to day 3 in the former planning horizon, which is day 2 in the current one. Therefore, at this decision epoch, this patient contributes 1 to X prime to KL1 in the state after the transition. The illustration in the previous slide was for the first line of this formula. Other lines can be explained similarly. Assuming the independence of the random elements in our model, we can write the probability of S prime conditional on S and A as the product of all elements of these random variables. The immediate cost associated with a given state action pair includes rejection cost, diversion cost, overtime cost, and travel time cost. The unit rejection cost for a referral of type K depends on the expected number of visits multiplied by the service time for that service type. This means the first term in the cost function is equal to zeta R times total rejection hours. In the second term, the unit diversion cost of a visit of type K depends on the service time for that service type. Thus, the second term in the cost function can be written as zeta Z times total diversion hours. The third and fourth terms are respectively zeta U times overtime hours and zeta Q times travel hours. The default values of the weight factors zeta R, zeta Z, zeta U, and zeta Q are 5, 10, 2, and 0.1 respectively. We assume that zeta Z is greater than zeta R because without this assumption it would not be worth rejecting any referral, as the expected rejection cost would always be greater than the total diversion cost of the expected number of visits. Diversions violate continuity of care and add additional costs of using an on-call nurse, which companies would rather avoid as much as possible. On the other hand, zeta U is less than zeta R. To minimize the number of rejected referrals, performing all visits for a patient in overtime should be preferred over rejecting them. And at the end, zeta Q is much smaller than zeta U to avoid rejecting a referral or diverting a visit due to travel time. We aim to serve any distant location if it's feasible within the shift length limitation. Let's have some definitions. A policy mu maps each state to an action. Infinite horizon MDPs require the evaluation of infinite sequences of costs at all states. The value function of a given state S under policy mu, denoted by V mu S, is defined as the expected sum of discounted immediate costs, assuming we start from state S and actions are taken based on policy mu. Here, gamma denotes the daily discount factor. A discount factor between 0 and 1 means $1 today is worth more than $1 tomorrow. It ensures that the value function in an infinite horizon MDP remains finite. We consider gamma equal to 0.99, implying that the influence of the discount factor on cost over the short term is very small. The optimal value function of a given state, S, denoted by V star S, is defined as the minimum of V mu S for all mu. According to Bellman's optimality equations, V star S can be obtained by minimizing the sum of the immediate cost and the discounted expected future cost with respect to the actions. Now let's discuss the approximate linear program. According to MDP theory, solving Bellman's equation is equivalent to solving the following LP for any strictly positive set of state relevance weights shown by alpha S. However, solving this LP is no easier than solving Bellman's equations because there is a variable for every state and a constraint for every state action pair. To improve the tractability of the LP, we approximate the value function with the following affine function of the state variables. The approximate linear program, or ALP, is created by using V tilde instead of V as in the LP model. In function 17, tau, rho, and eta represent the ALP parameters that we should find. The optimal values of tau, t, k, l, j can be interpreted as the marginal cost of an additional visit with the same indices. For rho, k, l, it is interpreted as the marginal cost of an additional new referral with the same indices. The ALP model can be seen here. Although the number of variables has become much smaller in this model, we still have a constraint for each state action pair. The column generation method for the dual of this model can be a good solution method. The ALP model has two additional sets of parameters that should be tuned: expected alpha of x and expected alpha of y. Expected alpha of y is not a sensitive parameter, and we set it equal to expected of y for each k and l. But expected alpha of x is a sensitive parameter. For simplicity, we set it equal to a constant epsilon for all non-zero indices. Therefore, we need to tune only one parameter here, that is the epsilon. Based on our observations, the optimal ALP parameters change as we vary epsilon. However, the number of different solutions is limited, and it's dependent to the number of service types, the number of regions along the diameter of the area, and the possibility of overtime work. The rejection cost increases and the diversion cost decreases with an increase in epsilon. When all referrals are rejected for a specific epsilon, we don't investigate larger values. Here is an example with one service type and no overtime. 4 different policies have been found by changing the epsilon value. When epsilon is equal to 0, there is no rejection but a large diversion cost. As we increase the epsilon, we reject more and therefore diversion cost decreases. In the last policy, all referrals are rejected. In this example, epsilon equal to 0.5 results in the best policy. Here's the algorithm we developed for tuning the epsilon. I illustrate to explain this algorithm in the next slide. The problem here is to search epsilon values from 0 to infinity to find all different policies. The challenge is we don't know the scale of numbers we should search for. It can be from 0.01 to 0.1 or from 0.5 to 1 or even larger. That makes the process a bit complex, especially because deriving the ALP parameters, considering each epsilon, and calculating the average value function is time consuming. We have used an iterative process in which the step size adaptively changes. Using a simple process, we obtain 2 initial values called epsilon 1 and epsilon 2. The step size is defined as the difference between these 2 values. The red rectangles represent for the different policies that we have found so far. By comparing the ALP parameters of epsilon prime, that is the average of epsilon 1 and 2, with those of epsilon 1 and 2, 4 scenarios may happen. In these scenarios, we may make the step size larger or smaller, or move forward with the same step size. Here's the dual of the ALP model called DALP and can be solved using the column generation method. The column generation starts by generating a feasible state action pair and adding it to a set called S prime. It then solves a dual model considering only the state action pair in S prime. Using the dual prices of the constraints in DALP as estimates for the ALP parameters, it identifies the most violated constraint in the primal ALP by solving the following subproblem model called SALP. The SALP minimizes an expression equal to the right side of constraint 18b minus the left side with respect to all state action pairs. When this expression is negative for a state action pair, it indicates a violation of constraint 18b. If 21 is negative, the resulting state action pair is added to S prime, and DALP is resolved with the updated S prime. Otherwise, the current estimates of the ALP parameters are optimal. With a set of ALP parameters denoted by pi star, the ALP policy determines an action for any given state by solving an approximate version of Bellman's equations. Why do we call it approximate? Because we replace V star with V tilde in the Bellman's equation. This model has some notable features, as shown in proposition 1. Based on only the ALP parameters and unit rejection cost, we can identify regions for which all referrals are rejected and also those for which all referrals are accepted without solving the ALP policy model. For example, in the picture below, you can see an area close to the depot that is completely white, indicating that we always accept patients in this area. The furthest regions from the depot are completely dark, indicating that we always reject patients in these regions. There is an intermediate area between these two for which we need to solve the model to determine whether to reject each referral. I can claim that our problem is one of the most complex problems solved so far using the ALP approach. Although the plain column generation method had been successfully used to solve the ALP model for multiple problems previously, it didn't work for the current problem. To illustrate the tractability of the column generation method for solving the dual of the ALP model of our problem, let's first recap some definitions. L is number of regions in the area, K is number of service types, expected J hat K is expected number of visits for service type K. For an instance with L equal to 6, one service type, and the average number of visits per referral equal to 3, it takes 1 hour to get the ALP parameters. When we increase the number of regions from 6 to 24, the execution time increases to more than a day. This prompted us to try a new approach. As mentioned before, initially we derive the ALP from MDP and then the ALP from LP. The typical approach was to solve the dual of the ALP with column generation. However, due to the complexity of our problem, we used a new approach. We found a closed form solution for a special case of the problem, which was much simpler than the general case. We then simplified the ALP for the general case, inspired by the features we found in the closed form solution, and solved the simplified ALP using column generation. Let's get to the closed form solution for the special case. Consider a scenario where there is no rejection, no overtime, the diversion cost is much greater than the travel cost, travel times are symmetric for each pair of locations, and service times are the same for all service types. If condition 24 derived from the proof for the closed form solution holds, then we have the following solution for this special case. It took me 4 months to find this solution and then a couple of months to prove it. A nice feature of this solution is that it can be easily explained intuitively. The pivotal element of this solution, based on which all other paths are calculated, corresponds to the last possible visit of a referral assigned to day 1 for each service type and location. I explain the intuition of this solution with an example. Consider patient 1 with type K from location L with a maximum number of visits equal to 4 and a care pattern of 1. As 3 visits have already been completed before the current visit, we have a +1 for the variable x1kl3. The green visit is the last possible visit assigned to day 1, whose corresponding tau star is a pivotal element of the closed form solution. Let's set this value equal to c. For patient 2 with the same type and location, only 1 visit has been completed before the current visit. Therefore, we have a +1 for x1kl1. Now we want to calculate the corresponding tau star for this visit. The marginal cost of this visit includes those of itself and its next probable 2 visits. We know that the third visit happens with probability pk3 and the fourth one happens with probability pk3 multiplied by pk4. So it makes sense to write the tau star of this visit as a sum of the expected discounted cost of the current and next probable visits. Let's get back to the closed form solution. In this solution, gamma to the power of t minus 1 means that we discount the cost of day t to day 1. This part means to discount the expected cost of the remaining visits to day t. This is the minimum travel time cost per service in location L. This is the minimum cost incurred by a new referral assigned to the last possible day. And eta has been obtained in the process of proving the theorem. According to the closed form solution, this holds for the special case when the condition 24 is satisfied. According to proposition 2, if this holds for ALP parameters in the general problem, then the ALP policy assigns an accepted referral to the first day or the last day within the wait time target. Okay, now let's jump to the first heuristic reduction technique. Here is part of the closed form solution for the special case. As mentioned before, all parts of the closed form solution can be derived based on the yellow part. The yellow part is technically a 2-index variable because the first and last indices are always fixed. Therefore, we can express the 4-index tau as a product of the green part, which is a known constant denoted by delta t, j, k, and the yellow part, which is an unknown variable. Assuming this holds for the general problem as well, we can replace the 4-index tau with the 2-index one in the ALP model. This variant and its dual are respectively called ALP2I and DALP2I. The dual model has significantly fewer constraints. This heuristic reduction technique is extremely helpful when either the number of days in the planning horizon or the maximum number of visits for each service type is large. Now let's discuss the second heuristic reduction technique that addresses the number of regions in the area assigned to the nurse. The larger the number of regions, the more precise the travel times in our model, but also the more computationally intensive. For a special case of the problem, we observe that regions with the same distance from the depot have the same ALP parameters. Considering this point in the ALP model of the general problem, inspired us a proxy problem with much fewer regions that surprisingly could reproduce the same ALP parameters, at least for the small instances we checked. In this proxy problem called P1G, we use a one-dimensional array instead of the original two-dimensional area. To create the 1D array, we merge all regions in the 2D area with the same distance from the depot into a single region. For example, in the figure, a single white region in the 1D array represents all 4 white regions in the 2D array. The distance of each region from the depot in the 1D array matches that of its corresponding regions in the 2D array. Moreover, the arrival rate for this region in the 1D array equals the sum of the arrival rates for its corresponding regions in the 2D area. The expected alpha x and expected alpha y for the proxy problem are calculated similarly. The ALP parameters for the proxy problem can be obtained using either ALP or ALP2I. These parameters can then be used to derive the ALP parameters for the general problem. Considering that all regions with the same distance from the depot have the same tau and rho parameters as their corresponding regions in the 1D array. This method of deriving the ALP parameters is called ALP1D or ALP1D2I, depending on whether ALP or ALP2I is used to derive the ALP parameters for the proxy problem P1G. With this technique, we need to solve a much smaller primal model and subproblem using column generation. Here we provide a numerical analysis for the heuristic reduction techniques. We have an instance with one service type and a 2x3 rectangular area. We determine the ALP parameters for 25 random instances generated by varying the service type characteristics, average demand, overtime limit, and epsilon using each of ALP, ALP2I, ALP1D, and ALP1D2I. We chose this small area because we couldn't solve larger instances with the original ALP in an acceptable time. Here are the results for these 4 approaches. The average execution time of the ALP without reduction techniques is more than an hour. With only technique 1, it decreases to 11 seconds, and with only technique 2, it becomes 14 seconds. Moreover, when we use both techniques, it becomes less than a second. Therefore, ALP1D2I is our best version. Interestingly, the application of the heuristic reduction techniques does not result in any loss of optimality for the instances considered. The resulting ALP parameters obtained by these variants were the same as those obtained by the original ALP. Let's get to the numerical results. We compare the ALP policy with 2 other policies we developed. The first is a myopic policy that represents current practice and disregards the impact of future referrals. This policy evaluates various decisions by explicitly considering the implications of scheduling all visits up to the expected number for current patients and new referrals. The second is the SV policy, which represents a scenario-based policy and is an adaptation of the heuristic presented in Demir-Bilek's paper to our problem. It simulates future referrals for a given number of days over multiple scenarios and evaluates various decisions by scheduling all visits up to the expected number for current patients, new referrals, and simulated future referrals. In all experiments except the last one, we have an area with 24 regions. We define the area diameter as the travel time in hours from point A to point B. We consider the myopic policy as a reference to calculate the percentage gap for each of the ALP and SV policies. The percentage gap between the estimated value function of a random initial state for a given policy mu and the myopic policy is given by this formula. It should be noted that the myopic policy is not the best policy in any of the instances considered in this section. In the tables provided in the next slides, the last 2 columns labeled gap percentage SD with sublabels ALP and SB report the average percentage gap along with its standard deviation for each of the ALP and SB policies. When the average percentage gap for only one policy among ALP and SB is bolded, that policy significantly outperforms the other with 95% confidence. When both values are bolded, no significant difference has been found between the two. Moreover, in the level column, the bold level represents the default level used in other experiments for instances with one service type. Alright, let's get to the results for special cases with one service type. We conducted multiple experiments to assess the impact of changing different parameters on the policy's performance. In the first experiment, we investigated 3 average daily demands of 8, 8.5, and 9 hours. We considered 2 scenarios, one with uniform referral rates across all regions and another with random referral rates for different regions. The ALP outperformed the other policies in these experiments. We didn't find a significant difference in results between these 2 scenarios, but the gap between ALP and myopic increased with rising demand. In the second experiment, we evaluated the impact of the distribution of the number of visits. In the deterministic scenario, we assumed the exact number of visits was known. In the second and third scenarios, we assume it followed the Poisson distribution and a discrete uniform distribution, respectively. While the SP policy outperformed the ALP policy in the experiment with a known number of visits per referral, the ALP policy performed best in the more realistic setting with an uncertain number of visits per referral. Furthermore, in the 2 scenarios involving an uncertain number of visits per referral, the gap between the ALP policy and the SP policy was larger when the number of visits followed a discrete uniform distribution with greater variance. The SP policy initially schedules the expected number of visits for each referral and adapts as needed. This approach makes the SP policy less effective than the ALP policy in managing undesirable diversions, resulting in higher overall costs, especially when the number of visits for a referral exceeds the initially anticipated quantity. Nevertheless, if the precise number of visits is known, this strategy offers an advantage over the ALP policy, which only schedules the next immediate visit. In the service time experiment, we evaluate the effect of 4 different service times per visit. The ALP policy performs better than the other policies in these instances, and the average percentage gap between the ALP and myopic policies decreases as the service time increases. The care pattern experiment examines performance for instances with 4 different numbers of days between consecutive visits. The results show that the average percentage gap between the ALP and myopic policies decreases with an increase in the care pattern. The ALP policy outperforms the SP policy for a care pattern of 1, but is dominated by this policy for larger values. Due to discounting, the larger the care pattern, the smaller the difference between the rejection cost of a new referral and the diversion cost of all visits associated with that referral. This mitigates the consequences of making unfavorable decisions to prevent diversions, particularly considering the myopic and SP policies. Furthermore, as the care pattern increases, the planning horizon for both the myopic and SP policies becomes significantly longer than that of the ALP policy. For example, for the instance with a care pattern of 7, the planning horizons for the ALP, myopic, and SP policies are respectively 7, 54, and 61 days respectively. However, this significantly increases the execution time of the myopic and SB policies, but assists them in evaluating various decisions in a more thorough and extended look-ahead manner. In the wait time target experiment, we evaluated wait time targets of 1, 3, and 5 days, and the ALP policy outperformed the other policies in these instances. In the diversion weight experiment, we investigated the effect of changing the weight of the diversion cost, zeta z, in the cost function while keeping the other weight factors equal to their default values given at the left side of the table. The larger the zeta z, the larger the average percentage gap for both the ALP and SP policies. Moreover, the difference between the average percentage gaps for the ALP and SP policies increases in favor of the ALP policy with increasing zeta z. Some companies may prefer to avoid diversions and therefore set the diversion cost very high. When zeta z is equal to 1000, very large value, the ALP policy succeeds in decreasing diversions to nearly zero, i.e. 0.02. However, other policies are not as successful in this regard. In overtime limit experiment, we checked the impact of 0 overtime or 2 hours of overtime. The ALP policy takes greater advantage of the available overtime capacity to reduce rejections than the SP policy and outperformed both policies in this experiment. In the last experiment, we checked 3 different values for the area diameter. As expected, increasing the area diameter increases travel time. In this experiment, the ALP outperforms the other policies. For instances with multiple service types, we randomly generated the features of each service type. The service time can vary among 4 different values ranging from a quarter hour to an hour. The care pattern has 7 distinct values from 1 to 7. The wait time target ranges from 1 to 5, and the number of visits can follow either a Poisson distribution or a deterministic pattern with means of 6, 8, or 10. Finally, the overtime limit is set to 2 if it's allowable. Okay, let's see the results for special cases with 2 service types. In the experiment with an uncertain number of visits without overtime, although the average care pattern is about 4, the ALP policy slightly outperforms the SP policy. Moreover, in the next 2 experiments with a deterministic number of visits per referral, the ALP policy demonstrates competitive performance compared to the SP policy, for instance with 2 service types, in contrast to its performance in those involving only 1 service type. This shows that the ALP policy can handle the additional complexity of having multiple service types better than the SP policy in most instances. In the general case with 2 service types, an uncertain number of visits per referral, and an overtime limit of 2 hours, the ALP policy is the best choice in 92% of instances, while the SP policy is the best in only 36% of instances. Here is some additional information extracted from the numerical experiments. As shown in the table, the execution time needed for tuning the ALP for instances with 1 service type is about 22 minutes, increasing to about 5 days for instances with 10 service types. Moreover, deriving the ALP parameters for instances with 1 and 10 service types takes about 7 seconds and 1.2 hours respectively. However, these processes are performed only once, and once we have the ALP parameters, we can generate the daily actions very quickly in less than a second. The SP policy has a parameter called threshold value, which is time consuming to tune, taking between 12 hours to 2 days for each instance considered in our numerical experiments. As a last point here, the ALP policy's overall average travel time for all instances considered is smaller than those of the myopic and SP policies by about 9% and 22% respectively. Here we have an illustration of the ALP policy properties. Consider the following example with two service types. For this instance, the gap between the ALP and myopic is about 16%, and that between the SP and myopic policies is 14%. The difference between the ALP and SP is significant with a 95% confidence level. In this picture, rejection rates in different regions are shown for different service types and policies. The darker the region, the higher the rejection rates. For the ALP policy, there is a completely white area close to the depot where all referrals are accepted. There is also a completely dark area far from the depot where all referrals are rejected. And between these two areas, there is a maybe area where referrals are sometimes rejected. On the other side, the myopic and SP policies may reject a referral very close to the depot and may accept a referral very far from the depot. Another point is that because the unit rejection cost for service type 2 is smaller than that for service type 1, all policies reject referrals with service type 2 more frequently than those with service type 1. Here we see the assignment dates for different policies. As mentioned before, the ALP policy assigns just to day 1 or the last day within the wait time target. For service type 1, it assigns to day 1 or day 3, and for service type 2, it assigns to day 1 or day 5. Although the other policies may assign to all days within the wait time target, they tend to assign to the later days. Regarding the diversion rates, all policies prefer to divert visits that are further from the depot. Okay, let's get to the optimality gap. To determine the optimality gaps for heuristic policies in minimization problems, it is necessary to obtain a lower bound on the optimal value function. A popular approach involves relaxing the non-anticipativity constraints, assuming perfect information about all future stochastic elements. Since our model is an infinite horizon model, to address the issue of simulating infinite sequences in the perfect information relaxation, a standard and equivalent formulation is used where there is no discounting. Instead, an absorbing costless state S bar is reached with probability 1 minus gamma in each period. In each sample of the perfect information relaxation, an absorption time T bar is revealed following a geometric distribution with a parameter 1 minus gamma, along with a sample path that provides all information about future referrals up to day T bar, including the exact number of visits. Then the following recursion must be solved for each sample path. Here, ST plus 1 represents the state ST after a transition, considering perfect information relaxation, and the value function for the absorbing state is equal to 0. Although obtaining this lower bound was intractable for our default instance with one service type, we managed to achieve it for a smaller instance with one service type using some tricks. In this instance, the service time is 1 hour and the wait time target is 1 day, meaning any accepted referral is assigned to the next day. Additionally, the number of visits for an accepted referral ranges from 1 to 8 with a mean of 4. We obtained 5 random initial states after warm-up period using the myopic policy and generated 100 sample paths for each of them. Then we solved the recursion for each initial state and each of its sample paths. To make the recursion tractable for this special instance, we defined the state ST differently, representing it by the rejection or acceptance status of each referral arriving a few days ago. the non-zero x values in the initial state that may affect the current day's decision, and the new referrals waiting for a decision on day t. We evaluated the ALP policy for each initial state when referrals arrived according to each of its sample passes. The resulting average percentage gap between the lower bound obtained by a complete information relaxation and the upper bound derived by the ALP policy was about 18%. One of the main directions for future research is addressing the multi-nurse version of this problem, which involves multiple nurses with different depots. Consider an example with 2 nurses and 1 service side. Let's assume that these are the rejection rates obtained by solving the problem for each nurse independently. The colors for the rejection rates are the opposite of the previous figure, meaning the darker, the more acceptance. Now we can perform this process sequentially and update the remaining referral rates based on the demand covered by the previous nurse. By doing this, the second nurse may be able to cover a larger area. This approach can serve as a starting point to develop a heuristic for the multi-nurse problem. Okay, thanks for your attention to this presentation. If you have any question, you can ask in the comments.